All right, this is algebraic reasoning, chapter 1.5, example 1. It says, Deanna dropped a basketball and let it drop several times. As it bounced, she recorded the height. The table below shows the average bounce height in centimeters of the ball after several trials. Okay, Deanna dropped the basketball and let it drop several times. As it bounced, she recorded the height. The table shows the average bounce height of the ball after several trials. So like this is bounce 1, bounce 2, bounce 3, bounce 4, bounce 5, all that sort of stuff. How many bounces, how high it goes. Alright, just calculate the finite differences between the successive rows. Okay, so finite differences. Negative 135 to 180, well that's down 45. This is down 35, this is down 25, this is down 20, this is down 5, 15, this is down 10. Alright, they're all vastly different. So does the data fit a linear pattern? No. Because the differences are not similar. Alright, so there's a difference between is a linear function and follows a linear function, okay? If it is a linear function, it's perfect. If it follows a linear function, they're close, and you can turn it into one to closely represent it. Alright, but this doesn't fit because they're very different. Okay, so let's calculate the ratios. Okay, so literally we take 1 and divide it by the previous. So 135 divided by 180 is 0.75. So this is a multiply by 0.75. 100 divided by 135 is 0.74. It's like 0.74074074, but we're just going to go 0.74. Okay? And then keep on going. I'm going to pause and just fill this in right quick, okay? And there they are. And you notice they're all really, really close. They're about 0.75, 0.74, 0.73. They're all very, very close. So, does the pattern seem to fit an exponential pattern? The answer is yes. Because the ratios are similar. Okay? The ratios are similar, straight up. Alright, the last but not least, calculate the average ratio between successive rows of the average bounce height. So basically, you add them all up and divide by however many there are. So if you want the average ratio, okay, that equals, add them all up, we got a 0.75 plus a 0.74, that's not a 5, that's a 4, plus 0.75 plus 0.73 plus 0.73 plus 0.75, and we are going to divide it by, how many other, 1, 2, 3, 4, 5, 6, 6. Now understand, remember, there are 7 items up here. You're right, don't divide by 7 because there are only 6 ratios. That's what we're averaging. Alright, I'm going to give me a second pause. Alright, I paused to put this in my calculator and I got 4.45 divided by 6, and you get 0.7416666666. So we're just going to do 0.74 for the sake of argument. That is your average ratio. Cool. Alright, I'm going to pause and go to the next page. Alright, so we got an average ratio of 0.74. I'm just going to write it over here so I don't forget it. You got your packet, you can always flip over, but it's kind of hard for me to back up in the videos. It says, what is the y-intercept for the situation? Well, the y-intercept is 180. And it says, explain your reason. Because x of 0 equals 180. That's your starting point, and that's your reasoning. All right? Build an appropriate model to fit the data. Well, it's exponential, so remember that's y equals ab to the x, where a is your starting point, that's your x of 0, your start, and b is your common ratio. Alright? So not b. So f of x, or you can put y, I really don't care, equals your a value, which is 180, times your b value, which is 0.74 to the power of x. erase that little tick. I really don't know what that's there for. Okay? Does the model represent exponential growth or decay? Oh, growth or decay. Remember, there's two ways of looking at this. We can either A, see if the data is going up or down, which in this case the data is going down, so that would tell you decay. It goes 180, like 170, 165, that sort of thing. Alright? Or you could look at the B value. So if the B value is greater than 1, or if the B value is between 0 and 1. If it's a decimal, essentially. So if it's greater than 1, this is growth. Between 0 and 1, that's decay. So since my B value equals 0.74, this is decay. And I'm going to say simply because B is between, and I'm just going to state the statement like that, between 0 and 1 is where B is. Now you could also say because B equals 0.74, you could also say because, you can also say as my X increases, my Y's decrease. My Y's are decreasing over time, that sort of thing. Okay? Letter G, use the ball model to estimate the ball's height on the 8th bounce. Okay, so that's Y, choose a consistent color. I'm using blue a lot. Y equals 180 times 0.74 to the 8th, and that is an exponent. Now remember, to get to an exponent in your calculator, right above the divide symbol is a button that looks like that. That is your caret. It's what it's called. I think it's spelled with a K, but it might be spelled with a C. I don't know. So when you type it, you'll do 180 parentheses 0.74 parentheses, and you'll go caret 8, like that. Okay. So I'll erase that in case somebody's just copying from that. 180 parentheses 0.74 close parentheses caret 8, and you get Y equals 16.2 centimeters. Okay. A basketball has a diameter of about 24 centimeters. What should be the last observable bounce? Well, I can't really back up and go, oh, I can. I got it right here on page. I got this thing printed out because I am ready to go. Well, think of it this way. She's measuring to the top of the ball, right? She's measuring the top of the ball, so it's at the first bounce, she's dropping it from 180 centimeters. All right? Or, since the ball is 24 centimeters tall, if you're just saying how high is it off the ground, from here to the ground is 80 minus 24 is 56. 156. It's only 156 centimeters off the ground. Okay? So if she's measuring to the top, you will never see an 8th bounce, according to this model. Because it's only, if it was 16.2 meters tall, here's the ground. That means the ball went like this. To get down to 16 centimeters, the ball would be partially underground. Does that make sense? Alright, so what you need to do is you need to go back to your chart and say, what's the last one that would work? Well, according to the model, x of 6 equals 30. The only one we need to check is x of 7. So again, stick in your calculator, 180, 0.74 to the 7th. That's 21.8. Again, shorter than the basketball. So the last observable bounce is the 6th bounce. Alright? And there you go.